system. In particular, where their number of variables were equal to number of equations, okay, n variable n equations, and the corresponding coefficient matrix will be a square matrix in that case. And then we discuss a few rules to solve. We discuss few methods to solve those system of equations. So some of them, yeah.
As I had followed the discussions, was just asking because of the name I'm getting confused. What does determinant part 1 contain and determinant part 2 contain?
You can check it on the web page. Okay.
In the web page, it is not written actually. Determinant part 1, determinant part 2. That is only written. I followed the discussion, but because of
I
the
think
name,
you haven't. So if you go to determinant 1, you will find out there is a video. Okay. There's a lecture video. You go to that lecture video. You will find out what is in determinant 1, what is in determinant 2. I think you haven't gone through.
No, I am attending the live session actually, the instructor.
No. Live sessions, there is no determinant 1 to determinant 1 and determinant 2. Like determinant 1 and 2 were in week 1 contained there. So I think you are getting confused between two things. Yeah.
Okay.
Yeah. So, okay. So I expect you guys to ask me questions related to which I'm discussing in the live session. Okay. If you have any other technical questions, like where is the portal, is this week 2 or week 3, please be aware of these things as of now. Okay. It's been the second week. This is the second session of the second week going on, and I expect all of you to be aware of all these things, and you shouldn't be asking all these basic questions which shouldn't even be a question at the first place. Okay. All right. Yeah. So if you guys have any questions from the Sunday's discussion, I will. So the floor is open. You may ask your question. If there is no more question, then we can go ahead with revising this Sunday's discussion, and then we can go ahead with the today's part of discussion. Yes, Bhumi.
So I just wanted to ask if the graded assignment after submitting, like week 1 graded assignment, the date has been completed, right? So will the doubts be cleared over here in instructor session or TA sessions?
You can ask your doubt in TA sessions. If you have any question, you can also ask me in instructor session, but it will be discussed once I cover today's material. If there is a time left at the end, then I can answer that question. Okay.
Okay, sir.
Okay.
No issues.
All right. Ranjit, Rahul, Ranjit, do you have anything?
Hi, sir. Good evening.
Hi.
Sir, just one small thing. When you're looking at this Echelon form and the gross elimination, right? Whenever you can find time, can we just look at the actual usage of this in the real time? Any small example would help.
Yeah. So I will discuss the where does it use.
Yeah.
So in large row echelon forms has many applications. One of the application is to find out the inverse of a matrix. Another application is to find out the determinant of a matrix. And if you want me to ask, if you are asking where does that determinant is used, where is inverse is used. So I think I have already discussed from where do we get system of the matrix. Why do we use matrix system? So it is basically to solve a bigger, larger picture in order to which consists of arranging data. Okay. And when you want to study that data, you need mathematical objects like determinant, inverse of the matrix, and all these things, because you have inserted your values inside a matrix. So if you want to understand the relevance of the data, or you want to understand some property of the data, which is preserved under determinant property or inverse property, so that you can distinguish two set of data or something like that. All right. That is where these techniques will be used. So in order to find out the determinant, row echelon form will be used. If you want to solve a system of linear equation, these Gaussian elimination helps you to write a code, because it gives you algorithmic way. In particular, it gives you an algorithm to solve a system of linear equation. This is being used in many software like MATLAB and many other software. Even in Google uses this to have his rank algorithm, which Google uses to solve search engine, which Google use in its search engine. Okay, so it has a lot of application, but if you want me to point it down where it is actually used, I can't help you with that. But yeah, but whatever you are learning in
Sorry,
this,
Google,
it
which
will be
algorithm use? Could you please repeat?
so rank. So Google use this rank arrangement, right? So it associates a rank to the data. So, and these ranks, how do we obtain rank? Because you need to enter data in some multi-dimensional array or something, and then uh, those on those you need to operate on those arrays. So they are like a higher dimensional version of matrix, and then there are corresponding operations, row operations. If you look at particular 2 by some cross section of that array, then you can apply, then you can reduce that matrix, big chunk of matrix. So
Sir,
that is
what
the
is
Excuse
previous.
me, sir.
rank is associated with? This association couldn't get it.
Yeah, so
What
I
is
don't know the
associated with
detail. If you want me to go into detail of what how Google
Okay,
does it,
okay. No,
I
since
don't
you're
have the
answering,
details. Yeah, but I'm saying basic linear algebra concepts has been used in preparing those algorithms. That is what the point is. Even MATLAB, and there are many other softwares which uses Gaussian elimination, row echelon forms to find out the determinant of a matrix, and to find out the inverse of a matrix. Okay, because you insert, let's say you insert a matrix in your system, and then you get the inverse of that. How does it do it? So there is some algorithm behind it. What does that algorithm use? That algorithm is based on Gaussian elimination or row echelon form or row reduction, which we will study in today's discussion. All right.
so
Excuse
just
me,
I
sir.
just want to confirm one thing, that this row echelon Gauss elimination we will use when the determinant of the coefficient matrix is 0.
Yes, but it's not. It doesn't stop there. You can always use for when it is non-zero also. So it is not the case when it is zero only. Then you will use, because what may happen is that if you want to use, if it's non-zero, determinant is non-zero, then you want to use some Cramer's rule, or you want to use inverse of inverse method, which I discussed in last session. But
Yes, sir.
then calculating inverse of a matrix which is not of 3 cross 3 order, it will be very hectic in computation. All right.
Okay.
So you want to find out some other way to find out the inverse and determinant of that. Let's say you have a 10 cross 10 matrix, and how will you find out the inverse of that? So there,
So for higher
these
order
row
matrix, we
reductions,
do the Gauss elimination.
not Gaussian elimination, we will do the row reduction. So let me start with the today's lecture, and then you will get to see all these
Excuse me,
things.
sir.
Okay.
Thank you, sir.
Hello,
Thanks. Yeah. Yeah, Avansh, you go ahead.
sir. Can you, sir, explain inverse of a matrix with example of 3 cross 3 matrix? At the end, A
So if you
x is
want
equal to
to
A
look at
inverse.
what is inverse, so I suggest you to go back to Sunday's lecture recording. It's available on YouTube also, and you can go to that, and then you will find out the I have explained over there. Okay. All right. Any other question related to? Yeah. So let me get started with.
No, sir, I get that, but last x is equal to A inverse B. I could not get it. So
Yeah.
can
Yeah,
you?
so you that also you can go back to previous recording. Na? Yeah, that is there. If you have any particular doubt in that thing, I can explain you that. But if you want me to discuss the complete theory, it will be
Sir,
difficult for you, because I
only
also need
n
to
part.
cover today.
N parts are answer this, that one.
It's a matrix multiplication. So you have A inverse. Okay, I will discuss in couple of minutes. Just wait. All right. So in Sunday session, we discuss a system of linear equation with n variables and n equation. What does it mean? It means that suppose you have a system of linear equation which is of, let's say, so this is a system of linear equation. Okay, so how many variables are there? There are three unknowns. Unknowns or variables, both are same thing. I will be using them interchangeably. There are three variables, and then there are three equations.
Sir,
So
I was disconnected. Could you please? We are starting with the row echelon. Could you please repeat? I just heard till that we are going to start, and after that I got disconnected.
so I'm currently revising what happened in Sunday. Okay.
Okay, okay, thank you.
Yeah. So there are three equations and three variables. So what will be the corresponding coefficient matrix? We have also seen that you can represent this system of linear equation in terms of a matrix. So the corresponding matrix will be of 3 cross 3 order, and it will look like this. All right. So this is called the coefficient matrix. All right. And then you can write down the variables in another column vector or a column matrix, and you can write down the entries, the constants on the right, also in a column matrix. All right. So this will give you a matrix presentation, which can we think of it in this way, where x bar and b bar are the vectors, the column vectors. All right. So this matrix representation is representing this system theory equation. So these both of these things are same, and this matrix is called the coefficient matrix. So this is what we have already known. Coefficient matrix. All right. Clearly, the order of coefficient matrix is n cross n. So now we discussed last time, if the determinant of the coefficient matrix is non-zero, that means the coefficient matrix is invertible. So we saw that if determinant of A is not zero, that is A is invertible, then you can find out solution of this system of linear equation by two methods. First one was the Cramer's rule. Okay, so Cramer's rule tells you that you need to substitute your constant column. You need to substitute your constant column with you need to substitute your constant column with in order to define these new metrics. So we define AX1 by AXI by removing the ith, by replacing the ith column with the constant column. All right. So in this case, so for example, in this case, let's say if I define AX1, and it will be 1, 2, 3, I replace the first column and the other two columns remain as it is. All right. Similarly, you can define AX2 and AX1 and AX3. You can also define. So the x2 is in the subscript. Okay, don't get confused that I'm multiplying x3 to this. All right, and then once you have these AXIs, you can find out the x1 by looking at the determinant of AX1 divided by determinant of A. X2 will be again the same, and so on. So in generality, if you have a larger system of equation where you have n variables and n equation, then you can define AXI to be determinant of AXI by determinant of A. All right. So this makes sense because the determinant coefficient matrix is of has non-zero determinant. All right. Otherwise, this won't make sense. Now, second method that we discussed was using the inverse of the matrix. Okay. Because A is invertible, because A inverse exists, I can use A inverse to find out the x. So what was the matrix representation? Matrix representation was AX bar is equal to B bar. Now I multiply A inverse both sides, and this will give me that now this will become I, and this will remain as it is. So multiplying I with X bar will give me X bar only. So this will be these. Now what is happening on the right hand side? You are multiplying two matrices. All right. So this is a 3 cross 3 matrix, and this is a 3 cross 1 matrix. So the matrix multiplication makes sense, and the resultant matrix will be a column of 3 cross 1. All right. So
Excuse me, sir.
yes.
The standard result is this, and I think you had only explained, but I have little forgotten that while deriving the standard result, why do we multiply the inverse with left hand side only? Why don't we do the right hand multiplication? Just briefly, could you please remind? It would be very helpful.
you can do it by your own also, because if you multiply it on right hand side, okay, by right hand side, what will you get? You
Yes,
will
yes.
get this. But this doesn't give you anything. This doesn't lead you to anything, right?
Okay.
Where does it lead you? It doesn't lead you to anything. It doesn't help you solve for x. In order to solve x, you need to multiply a inverse on the left hand side.
Okay. Okay.
All right. So that
Okay.
you can say that this is equal to I. All right.
Okay.
So this is how we can get x vector in particular. Uh, so suppose this will give you some vector c. So x vector, which is x1 up to xn, this is equal to some c vector, which is c1 up to cn. So this is how you will get a unique solution to this. All right. So this is what we discussed this Sunday. Now in today's topic of discussion, today's topic of discussions are, first we will look into the system of equation where which is of non-square type. That means it has m variable, n equations and n variables. Okay, so it will correspond to a coefficient matrix of order m cross n. Correct. Now we will look at some special type of coefficient matrix which are of these two, which are in these two forms. First, which is called row echelon form and row reduced echelon form. So if your coefficient matrix is in of this form, then how can we solve our system of linear equation? All right.
Sir, sorry, sir. Have we written m cross m or n cross n only? Like.
So I will suggest, if you guys have any question, please raise your hand first, and then I will let you speak. Okay. Yeah. So that would be better for me, because otherwise it keeps that if you keep on asking in between, so it breaks my flow also. So I will appreciate if you ask your question after raising your hand. All right. So yeah, so you ask me whether it is m cross n. So you tell me, if it has m equations and n variables, then how many? Then what will be the order of coefficient matrix?
M cross n.
Right. So that
Sorry, sir. I
answers
could
you.
not understand the handwriting. This was screen. Sorry, sir. Okay, sir. Understood.
Are others able to see my handwriting? Is it visible to
Yes,
others?
yes.
Yes.
Okay.
Yes, sir. Understood.
Okay. Thanks. If there is any problem with the handwriting, you guys let me know. I will write it more clearly. All right. Yeah. So I would appreciate if you guys have any question, please raise hand, and then I will answer each one of you. So don't worry that I will not going to answer, but it will help me to uh, uh, be in flow. All right. So yeah. So first we will see how to solve a row reduced echelon form and reduce row echelon form matrix, coefficient matrix, and row echelon form matrix. How to solve that and find out x1, y1, and up to xn. And then we will see how to convert a given matrix of m cross n order. All right. How to convert an m cross n order matrix to an row echelon form, as well as to an row reduced row echelon form, by using the operation called row reductions. Okay, so you can perform operations on rows of a matrix to obtain it in some specific form, which is of REF and RREF. Okay, this will help you to simplify your system of equation into a better form, and then you can solve it. Okay, and then we will also see one of the application of these row reductions. It will help you to calculate determinant of a matrix. Okay, because these row reductions preserves the determinant of the matrix. Okay, so whatever the intermediate matrix you will get after performing the row operations on it, or row reductions on it, the matrix will be preserved. That means the matrix before and the matrix afterwards will be same. And then we will look at Gaussian elimination method to solve a system of linear equation. All right. Yes, Bipul.
Sir, point number 3, we have M cross N and M cross N for REF and RLEF. So what is the
Yes.
difference between these two? Both are for M cross N, right?
Yeah, yeah. So they are different in look. So they have a different appearance. Okay. So so every row reduced echelon form is a row echelon form, but not the otherwise. So in order to obtain row reduced row echelon form, you need to do one more operation. Okay, so I will come to that. I will come to that. So this is just the introduction. Yeah. All right. So let's first start with what is system of linear equation, m equations, and n variable. How will it gonna look? So let's take some examples. So let's take 2 cross 3 setup. So that means there are two equations. So 4x1 plus 5x2 equal to 1, and x plus 4x2 equal to -1. Okay. Sorry. Yeah. Plus x3 is equal to 1, and this is equal to -1. Right. So this is a system. So how many equations are there? There are two equations, and there are three variables. All right. So it is of 2 cross 3 order because the corresponding coefficient matrix will be of 2 cross 3 order. So if I write down the coefficient matrix, then it will be 1, 4, 0. This is the coefficient matrix A. So clearly I cannot use the square matrix techniques, for example, the Cramer's rule or invertible matrix method to solve the system equation. I need to come up with something new. In general, if you may have some m cross n matrix or n cross m system, so that means what does it mean? That there are m equations equal to b1, yes. Is there any question? All right. So you have m equations and n variables, and the matrix corresponding to that will have order n cross n. So
Would that be
yeah,
M?
right. Thanks. And the variable matrix, which will be a column vector, so it will be of n cross 1 type. So it will be x1, x2 up to xn. And the constant vector will be again n cross 1 of this type. So this system of linear equation can be looked again by this, where this matrix is of n cross n, this is n cross 1, and this is n cross 1. So writing your system of equation either in this way or in this way, both are same. Again, as in the case of n cross n system. Yes, Dilip.
So I was just wondering if the M and N are not equal.
Yeah.
Then so the
You will get something like this, rectangular shape.
yeah. So the second matrix, no, the variable matrix, which has got the X.
Yeah.
It might just be deeper, no, than the coefficient matrix.
Yeah, it can be longer or it can be shorter.
Okay.
Depending on the length.
All right. So that doesn't matter.
It doesn't matter.
Okay.
As long as the product is defined, it doesn't matter.
Okay.
Yes, Nidish?
Yes, sir. Well, sir, you said that as earlier said that this equation can be turned into a rectangular matrix also, right?
Right.
Sir, before
this is a rectangular matrix. Sir.
Yes, sir.
Yeah.
Sir, you just shown a before example, right, sir? Having 2 into 3 matrix. Then for this x bar will be like a 2 into 1, right, sir?
It is 3 cross 1. Because 3 variables, right?
Oh, okay, fine, sir, fine. Sir, then the value, then the constant value will be 2, right?
Oh, sorry, it will be bn. Sorry?
Sir, then how you, sir, because I'm saying that A matrix is 2 into 3 and constant matrix is 2 into 1. How you used to multiply the both? Because
So
A,
no, look at
A
this. So
inverse,
you are multiplying coefficient matrix with the variable matrix, right?
yes, sir, for
So look at
finding,
this: 2 cross 3 and 3 cross 1. So rows, number of columns matching with the number of rows. So you can multiply. And
yes,
what
sir,
will be resultant? Resultant will be 2 cross 1. That is what we are getting on the right hand side.
yes, sir, for if the, sir, for the question we need to find the coefficient matrix, sir. Then we should, for finding the coefficient matrix, we need to multiply the constant matrix with the A inverse, right? A power minus 1. Then how it's possible?
Yeah, you cannot do that. That's what I'm telling you. You cannot do that because A inverse doesn't make sense. For inverse matrix makes sense for square matrices. Here the matrix is rectangular matrix, so it doesn't make sense.
Yeah,
So
then
you need
how
to,
we need to solve this?
yeah,
That's
so
the question.
yeah, so I will discuss. So that's why today's lecture is on that only. If you have a rectangular coefficient matrix, then how will be approach to the problem? So what are the other methods to solve the system? All right. So today we
Yes,
will
sir.
discuss. Right.
Sir,
Yes, Neil.
can we also, sorry, sir, can we also use this method for a square matrix as well? That is REF, RREF?
Yes. Yes, Neil. Do you have anything to ask?
Sir, in the final line, we have written B n cross 1, but that should be, I think, B m cross 1 because our matrix are m cross 1.
Yeah. M cross 1. Yeah. Thanks. Yeah, I changed that. It is B1 to BM. So it is M cross 1 matrix. It is not M cross 1. Yes, Mahima.
Sir, if the x1, x2, and xn matrix is written in horizontal form or as a horizontal matrix, then how would the b1, b2, and bm matrix be?
It's not going to be horizontal matrix. It is going to be a column vector, which has one column. If you write it in horizontal, then it becomes a row vector, which is not the case.
But can we also solve it in that way?
Then you need to change your whole convention. So we are following one convention. You need to change your whole convention.
Okay.
Yeah. So let's not do that because it will be confusing for you. So don't go into that much changing convention and these things. Let's just stick to one convention which we are following throughout this course. Yes, Darji.
Hello, sir. If we have a square matrix, then we, from the determinant, identify the solution is unique or infinitely many or not. If determinant is 0, then we have infinite or no solution. But what
Yeah.
about in the case of this rectangular matrix? But if we have homogeneous system of linear equation, then we have always 0 as a solution. Then sir says that if we have number of variables is greater than number of equations, then we have infinitely many solutions. Is there any something for linear system of linear equation only which is not homogeneous?
Yes, you will come to know. So let me proceed with the lecture. You will come to know. So we can associate different objects to this. Okay, so we will come to know that there is something called rank. Also, you can tell by rank how many solutions it has on all these things. So we will come to that in the later half of the course. You will come to know.
So, but
And sir, is there, how can we identify the matrix is linearly dependent or not?
What do you mean by matrix is linearly dependent?
Like if matrix is linearly dependent, if one row is combination of other rows, so determinant will come out to be 0. So how can
Yeah.
we identify this matrix is linearly dependent or not?
That is not called the matrix is linearly dependent. Okay, so that is called rows are linearly dependent. Okay, so there is a
Okay.
so it's not the matrix that is dependent, it's the rows that are dependent to each other. Okay, second thing, uh, so you cannot directly tell. Okay, so you can have some complicated matrix, so there is no direct method to tell. The direct method to tell is to find out the determinant of that matrix. Okay, if the matrix is 0, then you can tell that the rows are in rows are dependent. So it's the other way around, not the way you want it to be. Okay.
Okay,
So,
sir. Thank you.
Okay. Yeah.
Sir, but have we covered this homogeneous linear dependence? These are new term to me, sir.
We have covered homogeneous system of equations last time, and I have also discussed rows, combination of rows. Okay, so I think he is referring to that only. So in the last session, I discussed one of the property. If you can write one row in combination of other rows, then the matrix determinant will be 0. So if you can do that directly, then it is fine. But it is a difficult task to identify in a given matrix. All right. Okay.
Sir, one row as a combination of other rows, are you referring to the row elementary operations or is it something separate?
We will come to that. So suppose it also, you can also get from the row from this. No, row elementary operation doesn't give you that. And it will be one row will be combination of other two. So it is
No,
a
like
different.
adding one multiple of a row to another row. Are you referring to that or something else it is?
No, it is something else. Right.
Okay.
Not
sir,
just the addition, you can write down your one row in terms of other rows. That is what I'm telling.
Oh.
Yes.
Sir, regarding something one asked that for the homogeneous system of equation means the b is 0, but the number of equations and number of variables are different. In that case also we will have only 0 solution or infinite solution, or some other solution can come.
Can you repeat? If you have
Means for a homogeneous system of equation, the number of variables and equations, if they are different,
right.
In that case also we will have either trivial solution 0 or infinite solution, or
So
there
trivial
will
is always the solution. Zero vector is always the solution. That is the first thing. Second thing, if the number of variables is not equal to number of equation, then it can have infinitely many solutions.
means other than the trivial and the infinite, there is no other possibility even for no,
What do you mean
depend.
by other than infinity?
No, means
it will always have a solution. Look, zero vector is always a solution. So there cannot be. So there are only three possibilities: no solution, zero solution, or infinitely many solution.
Yes.
So no solution always, no solution cannot be true because zero is always there. Zero vector is always a solution. So you can either have zero solution only, or you can have zero solutions or infinitely many solutions.
Okay.
Now, if you have number of variable equal to number of equation, then it is unique solution, which is zero vector. If it is not, in the case of homogeneous system of equation, then it will have infinitely many solutions. Is that clear now?
Okay, sir. And just one thing I'm trying to ask, that expressing one row as a combination of other two rows, are you trying to refer to as that r1 dash equal to r1 plus 2 or 3, or is it different from that also? Which I think I got mixed.
Okay, so you are getting confused with all these things. You forget about row combinations. Okay.
Okay.
All right. Okay, so where were we? So okay, so I have already talked about what is the associated coefficient matrix in the case of m equations and m equations and n variable. And now let me write down what is a row echelon form. Okay. So a matrix is said to be in row echelon form if the first non-zero element in each row called the leading term called the leading entry, and it is equal to 1. All right. I will discuss examples. So let me just first write down this definition of this echelon form. Each leading entry is in a column to the right. So this definition might seem a bit lengthier and difficult to understand at the first glance, but you will get used to it.
Sir, extremely sorry, sir. There is some electric work going on in the whole building, so I got disconnected. The row equivalent form you were starting, could you please repeat briefly? Just now I got.
I have not said anything. Whatever is written, that's what I've just spoken. So you can just read it. And the third point is that rows with all zero elements. So I will discuss example once I've done writing this. So then it will be clear what I'm writing. Are below rows having non-zero entries. All right. So what does it say? So a matrix is said to be in row echelon form if the first non-zero element in each row called the leading entry is 1. What does it mean? So you look at your matrix. Okay, so let's take the matrix that I mentioned earlier. So this matrix 4, 5, 1 and 1, 4, 0. So look at this matrix. So and now let's apply these things to this matrix. So the first non-zero element in each row called the leading entry is 1. So is it the case here? First non-zero entry in each row. So first row is this, second row is this. So what is the first non-zero entry? It is 4 and it is 1. So you may say that it is true in the second row, right? That the first non-zero entry of the second row is 1, but it is not true in the first row. But it should be true in each row. All right. So this is not in echelon form. It doesn't satisfy the first condition itself. So let me consider a new matrix. So let me consider this matrix which satisfies the first condition. So that means, let's say, all right. And now you look at, so now consider this example. So now it satisfies the first condition that first non-zero element in each row called the leading entry is 1. So that is true. In each row, the first non-zero entry is 1. Correct. Now, what is the second condition? Each leading entry is in a column to the right of the leading entry in the previous row. Each leading entry is in a column. So this leading entry is in the first column. So look at this first column. All right. Is in a column to the right of the leading entry in the previous row. All right. So if I look at this first row, then it is already, there is no column right to it. There is no column left to it. Okay. So I don't need to worry about it. But if I look at the second row, so the leading entry in the second row should not be in the first column because there is already a leading entry in the first column. So it should be in the right of the first column. All right. So this doesn't satisfy the second condition. So what it should be the second leading entry should be in the second column instead of the first column. That is what it should be the case. All right. So this is not in row echelon because it doesn't satisfy the second condition, but this will be in this row echelon. Okay. So let me remove this thing, this matrix as well.
Sir, could you please tell it briefly again? I could not.
Yes, sir. In brief, can you please explain it?
Yeah. Okay. So what does it say? So let me write down the matrix that I have written before.
Excuse me, sir.
Yes.
Sir, the leading entry is always 1.
Yes, that is the first condition. Look at this. All right. Okay. So now, this matrix, are you all convinced that this matrix satisfies the first condition? Are we clear on that? Okay.
Yes, sir.
Good.
Yes.
Now look at the second condition. So what does the second condition say? Each leading entry is in a column to the right of the leading entry in the previous row. Okay. So what does it mean? Look at the second matrix. Each leading entry. So what is the leading entry in the first row? In the second matrix I'm looking at. Okay. So leading entry is 1. That is correct. Leading entries is 1 in both rows. That is correct. It satisfies first condition. Now look at the second condition. In the second condition, say each leading entry is in a column to the right of the leading entry. So if I look at the first leading entry, which is in the first row, it is in the first column. All right. Now there is no column left to it because this is the first column. So there is no column left to it. All right. So this condition does not apply to this first column. All right. Because there is nothing to compare with. Okay. We will be comparing with the column on the right. Now look at the second coefficient, second leading entry, which is the second leading entry, which is the leading entry in the second row. Now look at the column Now look at the column which is right to this column. So it is in the second column. So column right to it is yeah, column right to is in the left. That means read this again. So each leading entry is in a column to the right of the leading entry in the previous row. So previous row, that means for the second row, the previous row is row 1. Leading entry is in column 1. So it is in the second column, basically in the right of the first column. All right. So that is what it says. But whereas if you look at this example on the left hand side, so you see that the leading entries 1. Yeah, leading entry 1 is in the first row. That is fine. Second leading entry is also in the column 1, but it should be right to the leading entry through the column of the first leading entry. So that means it should be in the second column, or in the third column. Should be right in the first column. All right, that is what it says. Yes, Neil Chandra.
Sir, sorry, sir. Just one thing I'm getting confused. The very first thing we learned about this is that the leading entry of each row should be 1. Yeah, you told some time before. So, sir,
Yeah.
in the second row of the latest matrix, that 0, 1, 5, the first leading element is 0. So that itself should.
No. Leading entry is first is 1.
No,
What is a leading entry? It is a non-zero element. Look at what is written over here. First non-zero element is the leading.
Okay.
What is the first non-zero element? It is 1. All right.
Okay.
Yes. Muti or Rahman.
Sorry to disturb, sir, but where I can find the previous lectures, TA sessions, and all.
Okay, I think others can help with that. So you can find it on the YouTube channel also. That's there, or you can just go to the Seek portal. It will be there. Seek portal of the course. Yeah.
Okay.
And Meghna, what's your doubt?
Sir, the example that you have written 154015. My question is, can the second row be 001?
0. Yeah, that can be.
Okay. So it need not to be just immediate the next column. It can
No, it need not to, because it should be in the right of the first column of leading entry. It should be in the right of that. It need not to be in the next right. All right.
Okay, sir.
Okay. Good. Nidish.
Yes, sir. Sir, according to first these 2 points, can we say that the first leading entry should be 1 for every row?
Yes.
Then, sir, for 2 into 3 matrix, we're just assuming 154015. Can we say for 4 into 3 matrix 101 001 0001, like that? I'm just asking.
Yeah. That is a correct. That's a correct thing. That's in row reduce. That's actually in row Echelon. Okay. So now let me give a few more examples. Yes, Dilip, do you have anything to ask?
Yeah, just like 2 questions back, you said 001 in the second row is also okay, right? But
yeah,
can you have a non-zero like 051?
No, because the first leading entry should be, what's the leading entry in that row? It is 5, right? Because that's the first non-zero element, so it should be 1.
Okay.
Yeah. So that's the first condition, right?
All right. So the only thing that can happen before the 1 is a 0.
Yes. In a row.
All right. Thank you, sir.
Yeah. Good. Yes, Neil Chandra.
Sir, if the first row of the matrix itself is 001, then according to the rules, is any next row possible?
Yeah. It is possible, but
for the echelon form.
Yeah, but that's the third point. So if there is a 0 element, so basically rows with 0 element, that means all elements in a row are 0, then they should be below to every other row which has non-zero element. Okay, so we will place that row at the bottom of the matrix. Okay.
No, I am telling that the first row is 001.
001.
Yes, first row.
Okay. Yeah, so then it will not be in row echelon form because it will not satisfy the second condition. Yeah.
Okay.
But sir, it can be 0, 0, 0.
Whole row can be 0.
Yes.
It can be 0, but then it will not satisfy the third condition. Look at the third condition. It says rows with 0 entries, if any, are below rows having non-zero entries. All right. So if there is a 0 entry, 0 row, that means row having all 0 entries, then it should be at the bottom of the matrix. It cannot be on top of any non-zero row.
Yes, sir.
All right.
Yes, sir.
Yes, Joy.
Yeah, I had a doubt. Like, what if in the first row it is given as 0, 0, 1, and the second row it is 0, 1, any other number?
Yeah. So it's not in row echelon because the second row, what's the leading entry of second row? Second column is the leading entry of the second row is in the second column, right? Which is not in the right of the leading entry of the first row's column, right? It is on the
Yes.
left, so it is not in the. It is not satisfying the second condition, so it is not in row echelon.
So, like,
Yes,
is there any
Nitish.
way, can we like switch the rows?
Yeah,
in
we
order
can,
to...
we can. Yeah. So those are row operations that I will talk once I get over with these questions. Yes, Nitish.
Yes, sir. Sir, I think that the first matrix 154, 140 and 154015 both are same because according to me, example means considering 1 kg of apple, 5 kg of mangoes, and 4 kg of grapes cost, for example, 20 rupees, 200 rupees, and 0 kg of
No.
apples.
Okay. Let me stop you over there. What are you going with that?
Yes, sir, because if the condition comes under adding means it's like we can alter anywhere. Like the first matrix is equal to second matrix, right? You're just altering
It's not
the
equal to
zero
second matrix.
forward.
No. It is not equal to second matrix.
No, so we're just altering the third zero in the. We're just altering the second row of zero to the first, right? Then it seems like the same. We're just adjusting the values from one to previous.
No. They are not same matrix. So if whatever you are saying, you need to be. So you cannot just use an example and say that this setups is same as in that example. When you say in mathematically, you need to come up with some definition which puts both things in the same of the same type. Okay, there should be some equivalence. Okay, and there should be something equality needs to be defined. So it is not equal. It is even under the row reductions, they are not same. Under the row reduction also they are not same. So they are not even equivalent. So there is some notion of equivalency. We will come to know about that. So they are not equivalent.
Yeah, fine, sir. Thank you.
Okay. Yeah, it might be setting in your example accurately, but it is not correct. All right. If we are done with all the questions, so let me give a few more examples of row echelon forms, and then it will be more clear to you. So let's stick to this thing, 2 cross. Let's stick to this 2 cross 3 setup. So you guys tell me which of in the comment sections, in the chat box, you can tell me which one of the matrix is in echelon form. Okay.
Excuse me, sir. Chat is not available.
Sorry.
Chat is not available, sir.
I'm not able to understand what you're saying.
Chat is not activated.
Oh, chat is not active. Oh, thanks. Okay. Yeah, now you guys can message. All right, so I've given you 6 examples. So there are only 3 of them are in row echelon form, and 3 of them are not in row echelon form. Okay. Yeah. Right. So those who are saying option D is in the Echelon form. Yeah. So it's better you also write on chat. So it will be easier because if everyone start saying the answer, then it will be unfair to others. So let everyone understand what is going on. All right. So those who are saying D, that is incorrect. D is not in Echelon form. Right. So yeah. Neil Chandra, can you tell me why D is not in Echelon row Echelon form?
Sir, D is not in row echelon form because the first row is 100, but the second row, the leading element is in the first position only. It should be to the right of the column in the first row in which there is non-zero element. So,
Right.
but in D and the second row at the very first column only there
Yeah.
is
So
one,
it
which should
should
not
be.
happen.
Yeah, so it should be either in the second column or in the third column. That are the allowed columns where
Yes,
the
sir.
second rows. Okay, good. Yes, Dilip.
See to me, if you change the rows, like
Yeah.
remember.
After changing rows, it will be there, but as of now, it is not in rows.
Okay. So that is how you
Yeah.
check, is
So
it?
this matrix as it
after
is,
changing the rows,
as
the
a
matrix
matrix.
changes.
Yeah. So as a matrix, they are not row echelon form. They are not in row echelon.
Okay, it's the current situation that you need to analyze.
Obviously, I'm just asking for the matrix, whether these matrices are in row echelon or not.
Okay,
they are not.
Okay.
Sir, if you can identify all the ones, sir, I mean, I'm not getting.
Yeah. Okay. So this one is in row echelon. This one is not in row echelon. This one is not in row echelon. This one is not in row echelon. This one is in echelon. This one is in row echelon. Okay. So for example, this not satisfy first condition. First condition. This also does not satisfy. This does not satisfy second condition.
Sir, even A, if you see.
Oh, sorry. Second condition. Satisfy.
Sir, can you go one by one?
Yeah. So in the B case,
no, sir.
It does not satisfy.
First a second, sir. For the A case, we see in the
Yeah.
second row the one is there, but it is there in the third column. It is not in the second column. Then how can it be row echelon?
So which condition do you think it will? So what do you think? Which condition does it violate?
I got confused with. See, it should be on the right of it. Right of it in the second row should be second column. No.
No. Third column is also right of the first column.
Okay. That way. I thought. Okay. It is not.
It's not the immediate right column. It's not the immediate.
Okay. Second one is not satisfied. Yes.
Sir, could you please explain the E option? Say
E
first
option?
condition, yes, sir.
So
Your
E
first
option,
condition is satisfying, but the second one means in which we have to see the right side. That one.
Yeah. So there is only one leading entry, which is one, which is in the first row. There is no leading entry in the second row, right? Second row is 0, and it is at the bottom of the matrix. So.
Okay, sir.
Got it? Yes, Neelichandra.
Sir, I'm just asking that if the option E was the 001, 000, and then in the third row also there was the 000, then would it be row echelon?
You tell me.
I think it should be not, because from the definition what we learned that there should be only one complete zero row, which is preceded by other non-zero rows. But just
No. All the 0 rows should be at the bottom of the matrix. It doesn't matter how many. So it will still be in row echelon.
No, but if there are 2 0 rows, then if we see at the last 0 row, before the last 0 row, there is also another 0 row. So this contradicts the third.
No. It doesn't contradict. What does the third condition says? All the 0 rows should be at the bottom of all the non-zero rows. Okay. It doesn't matter whether immediate they are below the non-zero. They cannot be on top of any non-zero. That's what it says. It cannot be on top of. They can be below. It is fine. They cannot be on top.
So any 0 row means below any 0 row there should not be any non-zero row.
Yes.
But
that is what it says.
But above any 0 row there can be some other 0 row.
Yeah, that can be there.
Okay, thank you.
But there cannot be any non-zero at the bottom, below the 0 rows. All right. I hope these things, this definition makes more clear to you. Is more clear now. So now let me give you one more complicated, not complicated, but one more definition which adds up one more point to this row echelon form. All right. So I will copy this. So it is a row echelon form, and yeah, it is a row echelon form, but one more step at it, one more check at it, and then it will become a reduced row echelon. All right. So what is the check? So the just check is this. Let me is in reduced row echelon form. If all the three conditions that you have for row echelon form are there, and the third condition is this: whenever you have a column, okay, whenever you have a lead column in which there is a leading entry, okay, so in that column, that leading entry should be the only non-zero entry. All other entries should be zero. All right. So what it means is that, so in that case, A will not be in reduced row echelon form, but E is in reduced row echelon form, and yeah, only E will be in the reduced row echelon form. So what I'm saying is that if you can convert your A into some A prime, which is of this type, all right. So the leading entry in the third column, leading entry of the second row is in third column, and only that leading entry is the non-zero element in that column. Then it is the reduced row echelon form. Similarly, in case of F also, I can do that because that is also not in reduced row. So you can, again, the second row's leading entry is in the third column. If you can make this 3 go away, which we can by the reduce by the operations, we will be able to do that. Then it will become a reduced row echelon form. Okay, so let me write it down. Then I will answer your doubts, Sakhi.
Sir, could you please briefly explain again this, the reduced row?
Yeah, I will. Let me write down that fourth condition, and it will be clear to you. So for a non-zero, row, the leading entry in the row is the only non-zero entry in its column. All right. So what I said earlier, for example, so we saw these examples, 0, 1, 3, 0, 0, 1. So this was in row echelon form. Okay, everyone agrees to that. But this is not in reduced row echelon form, because if you look at the second leading entry, the column corresponding to this has non-zero entries other than 1. All right. So that is what it violates the fourth condition. Leading entry in the row is the only non-zero entry in its column. So, but this is not the case because there is 3 also. But I can make this into reduce row by applying the row operation. Okay, which I will discuss. You can make this 3 go away. Okay, and you can have zeros by some row operations, which I'm going to discuss. All right. So then the matrix on the left, the matrix on the right becomes reduced row operation, reduced row echelon. Okay. So in short form, I will be writing my reduced row echelon form as RREF, and I will be writing my reduced echelon form as REF. All right. So this is a small convention which I will do. Okay.
Sir, both the forms are only for rectangular matrix.
No, they can be M and M can be anything. Okay, it is independent of M and N. They need not to be rectangle. They can be square. They can be equal. Right. Okay. So yes. Yes, Sakshi, you can ask your doubt now.
Thank you, sir. Sir, here you are converting non-zero like 3 into 0. But in starting, if there is 0, 1, 1, will it be converted into RREF?
0, 1, 1.
Yes.
Yes, because what it says that uh, only one should be the in the leading entry column. Only that leading entry should be the non-zero entry. All other entries should be 0 in that column. Okay, it doesn't matter whether we have 1 over here or something else. So we will.
Sir, by this it will disrupt the second row, na?
No, it doesn't. Second row.
Like in the third column, it will become 1, 1.
No, I don't. What is your? Can you repeat your question? Maybe I missed
Sir,
it.
my question is, if you instead of 3 there is 1, then
Okay.
you try to convert it into RREF form.
Okay. Suppose there is 1. That's what.
Yes.
Okay. Then you
And
can
you
still
try.
do the row operation. So I will tell you what row operation will you do. You will remove R1 minus R2. Okay. You will change your R1 by R1 minus R2. So you will get 0 back. That is what you do.
Oh, thank you, sir. But means you are gonna perform different operation.
Yes. That is what I will discuss.
And sir, for every REF, RREF, there should be REF, na?
Yes. Because first you will
Okay.
obtain REF form, and then from REF you can go to RRE. So first we will always obtain an REF form, and then we can go to RRE.
Sir, please just once, please explain the third point. I am confused in that rows with all zero element. Just
Yeah, so
last time.
all 0 rows, okay, rows with 0 entries, they should be at the bottom of the matrix. That means on top, so there cannot be any non-zero row below the 0 row in REF or RREF. Okay, that means what I'm saying is that this is not allowed. Uh, this is not allowed. This is not allowed. Okay, this is not allowed. All right. So all the 0 rows below, non-zero rows cannot be at below a 0 row. Okay. All right. A lot of questions. Okay. So Saumarg, if I'm pronouncing your name, Saumarg.
Yes, sir. Yes, sir. Reduced echelon form and row echelon form are the same.
No, they are not same. I just explained the difference. Right. Look at this. Are these two matrices looking same to you? No. Right. All right. Yes, Darji J. Yeah.
Which two are you talking about, sir?
Look at
May I?
this matrix and this matrix. They are not same. Are they same? They are not same matrix.
No,
So
no, I am telling
reduced,
that reduced echelon form and row echelon form, are they both same?
Oh, sorry. Oh, okay. Sorry, my bad. Oh, yeah, it is maybe by the way I have written. Row echelon form. Sorry.
Okay.
This is earlier matrix is row echelon form. Sorry, my bad. Yeah, thanks, Omar, for pointing this.
Okay, sir. Thank you.
Yeah. Sorry for the confusion, guys. Yes, Darji J.
Sir, similar to row echelon form, do we have any column echelon form?
No, we don't. We will work with row echelon forms.
Only row
all right.
echelon form.
Yes.
But sir,
Yes,
we have column elementary operation similar to row elementary operation.
there are, but we will not be dealing with those. So let's stick to row operations only.
Is,
All right.
is there any constraint that to convert a matrix into RRE or RREF form, we cannot use row echelon form, row elementary operation and column entry operation both together?
No. We cannot do that. Only row operations we will perform.
Okay.
Yes. Because column operations make sense when you work with it will not lead to something which correspond to a solution system of equations. So if you want to correspond to that, then we will only stick to row operations only. All
But
right.
sir, if along with row elementary operation, if I use column elementary operation, then it makes my process easy. I can
But you will not
convert
get the
it
correct
into.
answer. You will not get the correct answer. So we will only discuss the row elementary forms. We will not go into the column operations. Okay.
Okay, sir.
Yes, Dilip.
So I wanted to ask you, how does that one in row 1 and column 3 become 0 in the next matrix, which is RREF? Is it by subtracting column 3 from column?
No. We are not subtracting column.
R1 minus R2.
We will be performing operations on row. So we are changing R1 to R1 minus R2. I will discuss these row operations. You give me some time.
Sure.
I will discuss all these operations.
Sure. Thanks.
Yeah, I am supposed to cover all these things in today's lecture. So just be patient, guys. I will discuss all these things in detail. Shelly, you may ask your question.
Yes, sir. Sir, in RREF, is all the leading coefficient should be 1, leading entry.
Yes. RREF is a row echelon form with one more condition added. So every matrix in RREF is already in REF form. Okay.
Sir, the rest conditions are same, no? In RREF.
Rest of the conditions are same except one more condition added to it.
Okay,
Yes,
sir.
Nitish.
Sir, according to RREF, we can say that the entire matrix should be consist of zeros and ones.
No, it need not to be.
Sir, but you said that.
Oh, let me give you an example. Look
Yes,
at this matrix. 1, 2, 3, 0, 0, 0, 0, 0. So is it in REF form?
No, sir. As it's in the REF form.
Is it in RREF form?
Yes, sir.
So here you go. Okay, Abhishek, you may ask your question.
Okay, thank you, sir.
Abhishek?
Sir, is it necessary to reduce all the non-diagonal element to 0? Hello?
No, it's not. It's not always the case that you will be deleting. For example, look at this.
Okay.
No, it's not
For
necessary. For
example, if
example,
I
the
take
example that I just gave. Look at this. It has non-diagonal entries. Okay, so you are not going to remove them, right? So this is an example, but this is an RREF form. This is an RREF. So,
okay.
It's not always the case. Okay.
Sir, but the rows after the first row, they do not have any one. Means the first leading element in the first row is only 1, and other all rows are 0. So how is it REF at all?
Why it is not in RREF?
No, the example.
What condition does it violate? You tell me what condition does it violate, and then
it violates the condition that point to that each leading element should be to the right of the column of the leading element of the previous row. The one example you just erased.
So what are the other leading element? Can you tell me what are the other leading element of other rows? Is there any? There is no other leading element.
Means in the each leading element should be to the right of the previous row's leading element, but in second row there is no leading element only. So
that condition does not even apply to it, right?
Okay.
Right. So it is vacuously true. That is what we call in maths. It's vacuously true.
Okay.
All right. After a lot of confusion, I think we are in situation to move ahead. Yes.
That was
Abhishek.
not in RREF.
Yes, Abhishek.
Sir, if my leading coefficient means diagonal is my leading coefficient, then all the non-diagonal element will be 0.
If your leading coefficients are if
In
all
that
the
case,
diagonal elements are leading coefficients, so first of all, diagonal elements
is
make sense in square
diagonal.
matrix. Okay, diagonal elements make sense in square matrix, so you are working with square matrix. Number one thing. Second thing, all the diagonal entries are one.
Okay.
For and then yes, then in and if the matrix is in RREF form, then yes, all the other non-diagonal entries will be zero. All right. Yes, Hiba, Sinein.
Yes, sir. So identity matrix, it could be a form of REF, right?
Yes, identity is an RREF. All right. Okay, lot of questions. Good, but we have less time to cover today's thing. Okay, so let's go faster. All right. So now let's see how to convert a matrix into an RREF form and REF form, which we guys are all are waiting for. So we
Sir,
can
sorry,
perform
sir.
three
At
operations.
the above the linearly dependent to explain. Actually, I was writing the point, so I could not hear. Just could you
Linear
scroll above?
independent.
Could you just
I
scroll
didn't even
above?
discuss linear. No, I didn't discuss linear independency.
No, just one second. Could you please scroll above? The system independent and dependent variables. That part could you please tell? Actually, I
Yeah,
was writing.
I will come to that. I have not discussed. I will come to that once I
Okay,
discuss
okay.
these
Thank
row
you.
operations.
Okay,
Yeah.
sure, sir. Thank you.
Yeah, yeah. Okay, so let us discuss how to convert a matrix into an REF and RREF form. All right. So there are three operations that you perform on a matrix and any combination of that. All right. So what are these three operations? So these three operations are right. Right. So first is interchange two rows. All right. So like in the previous example, we saw that you have a matrix of, let's say, this type. Then you can interchange R1 with R3, or let's say with first of all R2, then you will get this over here, and then you can interchange R2 with R3, so you will get over here. All right. So interchanging two. So I perform interchanging twice, not once, twice. All right. Now, scalar multiplication of a row by T, by a real number, T in R. All right. So let's say you have this matrix. So you can divide R3 by 3. Okay, you can perform this row operation that R3 divided by 1 by 3 R3. Okay, you perform this operation, and what will you get? You will the row third row will be divided by 3, so you will get 1. All right, so this is how we can convert. So any so in particular, how will you write this? You will write it like Ri changes to some multiple, real multiple divided by Ri, multiplied with Ri. All right. So
Excuse me, sir.
yeah, just let me finish this and we can ask you. Adding multiples of a row to another. All right. So what does it mean? So it means that suppose you have okay. So let's say you have this 2 cross 1 2 cross 3 matrix, and you want to convert this into RREF form. So how will you do that? So you can you can perform this operation. You can convert R1 by subtracting R2 from it. Okay, because what's the only point that is stopping you? That second leading entry, which is in the second column, has one as non-zero element other than the leading entry. So you can subtract R1 minus R2, and you can get this 102, sorry, 10, and 2 minus 3 will be -1, -1, 0, 1, 3. All right. So this is what you get, and then this is in RREF. All right. So now any combination of these three operations, interchanging two rows, scalar multiplication by a row, scalar multiplication to any row, and then adding multiples of one row to another. Okay, these combination you can use to convert any M cross M matrix to a row echelon form or row reduce or reduce to echelon form. Yes, Neil, you can ask your question.
Sir, two questions. First question is in the interchange two rows point, when we interchange the two row like R1 with R2, that is an odd number of changes. So shouldn't we include a minus sign outside in that step?
We are not calculating determinant. That is for determinant.
Oh, means in matrix, if we are doing that, we don't have any sign.
No.
And these matrices also defined also, means when we perform the change R1 R2, then it is not the same matrix anymore.
Yeah, we will get a different matrix. Obviously,
And
they are not same.
Okay, sir. And the second question is that in the third point, means if it has to be RREF, then every leading element that is there, that should be the only non-zero element in that column.
Yes.
It means in the second column, means I was thinking that it should be that it is 0, 1, 3.
That's the fourth condition. That's the fourth condition.
Yes, means the leading element of the second column is 1. So 1 is in the second column. So in the second column, if it had to be row echelon RREF, then it should be the only non-zero in that second column, like 0, 1 or something like that.
Yes.
And similarly, if it had a third row where in some other position there would be 1, then in suppose in the third column we would obtain 1. So in the third column also that 1 should be the only non-zero element.
Yes.
For every row we should follow this point.
Yes.
Okay. Thank you, sir.
Every row which has leading entry.
Okay, thank you.
Yeah. So the leading entry column will only have that leading entry as non-zero element. Other entries should be zero. Yes, Bipul.
Sir, in the point number 3, we wrote adding multiples, but we did subtraction, right? So is it?
Yeah. So adding multiple, if you take multiple to be -1.
Pardon me, sir.
You take your multiple to be -1. -1 is also multiple of R2. So you can think that it has like R1 plus -1 times R2. All right.
Okay.
Yeah.
But we can subtract as well, right? One row from another.
Because subtraction is also addition only.
Okay.
So it is
that way. Okay. Sorry, sir.
Yeah. No, nothing to sorry about, but okay. Yeah, that's how we write in mathematics, because all right. Okay. So good. Okay. So everyone seems comfortable with all these operations. So you can convert any M cross N matrix to an RREF or REF form. Okay. So now quickly let me tell you this thing, that if you have a system of equations whose matrix itself is in the RREF form or REF form, all right, so then how you can solve that? So for example, let's say you have a matrix system of equations which is given by this is equal to 1, and then x2, and then x3 plus x4 is equal to 5. All right. So if you look at this system of equations, so how many equations are there? There are 2 equations, and then how many variables are there? There are 4 variables. Right. So it will be a 2 cross 4 matrix. So let me write down the corresponding matrix. So it is 1, 3, 0, 0, and then 0, 0, 1, 1. So this matrix is in RREF form. Okay. Now, how do I obtain solution of this? So we can directly, so the leading entries of the Gaussian matrix, if it is an RREF form, these leading entries are called the dependent dependent variables.
And this is for
And then
REF only, or both REF and RREF?
Let's stick to RREF or REF. You can work with either of that, but let's work with REF form. RREF form. And then all the non-zero entries, all the other variables which are not dependent are called the independent variables. All right. So why they are called independent dependent? Because now what you can do, so because this matrix is in this form, is in REF form, what you can do, you can solve your leading entries, variables at the leading entries, corresponding to leading entries, in terms of independent variables. For example, x3 is equal to 5 minus x4. All right, from this equation. And similarly, x1 is equal to 1 minus 3x. So that's why x1 is called dependent, because it is dependent on x2. So that's why it is dependent, and x3 is also dependent. So leading entries of rows will become the dependent variables, and all the other variables will become the independent variables, because you can write dependent variables in terms of the independent variables by writing this equation. All right. So first, what we will do, so we will convert. So we will start with a matrix system of equation. We will convert it into. So we will start with the system of equation. All right, which will be AX is equal to B bar. Okay, we will convert this M cross N matrix to a. Then we will write this matrix in an extended matrix form, which will be given by this, and it will have n plus 1 columns, because we will add one more column to this matrix A, and we will call this matrix the augmented matrix, and then we will apply the row reduction operations, these row operations, okay, such that our A becomes an RREF matrix. All right, so that our A becomes an RREF matrix, and these row operation will also affect this column, the last column, okay, which is coming from the constant. So this will also affect this, and it will give you some B prime. So at the end, after applying these row operations, we will get matrix R, which is in row reduced echelon form, and matrix B prime. And once you have this, you will have dependent variables and independent variables, because you have converted it into RREF. So you have an independent. Now you will solve independent variables in terms of. Now you solve dependent variables in terms of independent variable by writing it back into Rx is equal to B bar. Okay. So whatever the solution you will get over here, whatever the solution this system will have, they are equal to the solutions of this original system. Okay. So this method is called the Gaussian elimination. So this is called the Gaussian elimination. And in Gaussian elimination method, we will use the row operations. Okay. We will
Sir,
use
could
row
you please
operations.
briefly tell again? I could not. Like
So what?
How to get the augmented matrix, and after the augmented matrix, what we are doing, that I could not get.
So till you understand this point, augmented matrix. So given a system equation, we can obtain an augmented matrix. Okay. Augmented matrix by adding the constant column into the original matrix. Okay. So this will give you
We are
n cross n
forcefully
plus
adding
1.
that column.
Huh?
Like we are forcefully adding that column.
What do you mean by forcefully?
Like just like that, we are including the
We
another
have consent of constant column matrix. We can add that. It's not forceful. Like,
okay.
Because we
And
want to
after,
solve that. So it's not
so
nothing is
after the
forceful.
augmented matrix, the steps could
Yeah,
you please
once we
briefly
get the augmented matrix,
Yes.
now we aim to convert our coefficient matrix into an RREF form. Okay, so we convert that into an RREF form by applying row operation that we just discussed. Okay.
So, sir,
And
why are we doing this? Are we doing this to get the solution to the system
Yes.
of linear equation,
Yes.
right?
Yes.
So, sir, 1 second. For a square matrix, we are using Cramer's rule and invertible matrix, and this is for a rectangular matrix. And with all
this can also be applied to square matrix also.
It can also be
need not
applied
to be.
but the objective is to find the solution to the system of linear equation, right?
Yes.
Okay, sir.
Because when matrix is in RREF form, just let me finish. When matrix is in RREF form, then we have seen that it is very easy to find out the solution, as in this example. All right, when it is in RRA, you can find out solution easily. So that's why our aim to convert it into an RRA. Yes, once it is an RRA form, then we get a new system of equations, and then we will solve the system. All right. Now, Neil, you can ask your question.
Any advantage
When
of
we
doing it
are
in that
converting the means after getting the augmented matrix, when we are converting it into the RREF, we have to keep the column B intact, or we have to include column
No,
B
no,
in
we will
the.
also perform the same operation on B.
And sir, what does the vertical line represent between A and B? Means what do we
Just
have to
to
do by
separate
that?
that, it is, we are separating that on the left we have a coefficient matrix, and on the right we have the constant matrix, just to separate that.
Okay, thank you, sir. And after we done the operation to convert A into RREF, and according to that B also changed. Then after that, what did we do?
Yeah, we will convert it back into a system of equation. We will write it like this, and then we will solve. So we will get the system of equation like this, which will correspond to the RREF form. Okay, whose coefficient matrix is in RREF form, and then we will solve this system.
And the solving we'll do by the Gauss elimination method.
No, solving. This is called the Gaussian elimination. So
Okay,
whenever you have coefficient matrix in RREF form, it is simple to solve, as you saw in this example. All right, you can write leading terms in terms of you can write dependent variables in terms of independent variables by directly substituting. Right, you can just substitute x3 is equal to 5 minus x4, and x1 is equal to 1 minus 3x2. So you can directly do that. That's fine. Yes, Shelly.
So the augmented form is for every system of linear equation, means for unique solution, finitely many solutions, and all.
Yes.
Okay, sir.
Yes,
Sir,
Bipul.
go a little down, sir. A little scroll down. I have one doubt coming on your page.
Yeah.
Sir, Ax is equal to B. We are converting to Rx is equal to B. But why are we doing it? We can directly solve it from Ax is equal to B as well, right? What is the advantage? I'm just thinking aloud. I mean, why are we doing this entire method?
Yes, it has a lot of advantage. It has a lot of advantage because solving this system is difficult. What will you will do? You will what method you will use? That is what we are just doing in this way, but it is more sophisticated.
Okay. So
if you have a larger system, let's say 4x4, 4x5, or some 10x10, then it will be very difficult. But this is algorithm to reduce this thing. This is algorithmic way, so that you can also feed this into computer, and then you can get results out of computer.
Okay, so
this is algorithm.
Rx is equal to B is the easier or the simpler form of Ax is.
Yes, it's a simpler form of the matrix here, but having the same solution. They have the same solution.
Okay,
that's the advantage.
Thank you.
Okay. Yes, Mahima.
Regarding that scalar multiplication, can we multiply all the elements in a row by 0?
No.
Excuse me, sir.
Zero row multiplication is not. It should be non-zero. Yeah.
Sir, I'm not able to get the last topic. Please explain this. After independent and very.
Yeah, I will.
Sir, can you take an example?
Yeah, I will do that. Just give me a minute. I was there. I was discussing an outline of what we are going to do. I was about to do that. Okay. So I will discuss this at the last, how we use row reduction to calculate determinant. All right. So whatever row operation that we discussed here. Okay. So you see there are row operations, interchange of rows, scalar multiplication of a row by a multiple. Right. So these operations, as we have seen while discussing determinants, we have seen that these row operations are preserves. These row operations preserve the determinant. In particular, switching rows will give you -1 sign. Right? Switching rows will give you -1 sign, but if it is performed multiple times, right? If it perform even many times, then it gives you the same matrix. Similarly, the scalar multiplication by a non-zero constant. Okay. Scalar multiplication by a non-zero constant will correspond to scalar being multiplied to the determinant. All right. So this operation. So let's say if this is A and this is B, so determinant of A is equal to minus the determinant of B. that we have seen. If you perform on a square matrix, all right. Similarly, if you perform the row, if you multiply a constant to to any row, then it is same as multiplying t with the determinant of the resultant matrix, and then adding or subtracting rows does not change the determinant. That is also we have seen that change of this type does not change the determinant. So determinant of A will remain as it is, determinant of B. So these three operations, if you performed all together, okay, they will. So what they will do? Yeah. So their effect in total will not change the determinant of the determinant of the resultant matrix. Okay. So I'm not going to do the proof of that. Why will it do that? But it will not change the determinant. So you can use these row operations to calculate the determinant as well.
Sir, when we obtain the system Rx equal to B, then how to solve that? By the normal method only, or again we have to apply the Gaussian elimination? Like
Sorry?
after converting A to the augmented matrix, also changing the column of B according to the operations, and then, as you said, when we finally obtain the Rx equal to B, then the Rx
Yes,
equal
yes.
to B, how do we solve?
Yeah, that you can solve directly because it is in simpler form. You can just directly solve. You can just write
Directly means
everything in terms of independent variable. You can write dependent variables in terms of independent variables. Independent variable, there will be some independent variable. You can write down your leading terms, leading entries in terms of independent other variables directly by the system.
Okay.
You don't need to do it. Okay.
Excuse me, sir. Can you explain, sir, a Gaussian elimination method once again, please?
Yeah, I will come to. Let me just finish with this. We'll use the row reduction to calculate determinant. So let me take an example. Okay, that will be good. So let's consider this example. Yeah. So let's consider this example. So because we calculate determinant for a square matrix, so I will start with the square matrix. All right. Now, let's say this is my matrix. Now I want to convert it into a row echelon form. Okay, reduced row echelon form or row echelon form, whatever it is, we can use either of that to calculate the determinant. So first, what we want to do, we want to make a 1 over here because first row leading entry should be 1 at the first column. So how we will do that? We can divide it by 2. So we can divide R1 by 2, and we will get 1, 2, 1 by 2. All right. Other rows remain as it is because we haven't performed any operation to them. Now, 1. Now, other leading entries should be in the right of this first column because my first leading entry is in this first column. So other leading entry should be in the column right to it. So we need to make all these entries to be 0. Entries in this column below to this first leading entry. Okay. So let's do that. So how do we do that? So I will remove 3 R2 minus 3 R1, and I will change R3 by 5 R1. All right.
Sir, I'm so sorry, sir. Just one thing. In the first step, sir, sir, in the point number 1, 2, 3, we spoke about interchanging row, scalar multiplication, and adding. But you have divided this. So division is also one of the rules, is it?
It is a multiplication, right? It's a scalar multiplication.
Okay.
1 by 2 scalar multiplication.
Oh, 1 by
multiplied
2. Okay. I'm so sorry, sir.
Yeah. So now you remove 3 times of R1 from R2. All right. 3 times of R1 from R2.
Sir,
So
we are
let's do
doing
that.
this just to make the element below 1 0 to satisfy
0.
the condition
Yes.
of like in REF or RREF both means if the below
Yeah,
the
because
leading entries the other should be 0.
yeah, because there cannot be another leading entry below the leading entry. Other leading entry should be right to the right of that. So all the entries below the leading entry should be 0. Okay. So now let's do that. So what we will get? We will get 0, 2, 11 by 2, and 0, minus 4, 13 by 2. All right. Now you do one more operation. Now the second leading entry will be in the second row. All right. So let's say we will have second leading entry here. So we will make this to be 1. So let's do that. So now divide R2 by 1 by 2. Okay, let's multiply R2 by 1 by 2. So we will get 1, 2, half, 0, 1, and then 11 by 4. All right. Third row remain as it is. And now we need to make this 0. So we will divide, we will subtract R2 minus 2, R2 plus 4, R3 plus 4, R2. So just keep in mind, one step, you only perform one row operation. Okay, don't perform two row operation at once. Okay, otherwise you will end up, you will do some mistake, or it will be wrong in some sense. And you cannot perform, and if you are performing two row operation at once, suppose, okay, which is not allowed, because it will lead you into some trouble. That's why I'm saying it is not allowed. If you are doing, let's say, two operations at once, then make sure that both of the operations are not performed. Let's say you are performing operation on R2, and then the second operation should not involve R2. Okay. All right. So you can
Sir,
perform
to be on
two
the safe
operation.
side, every row operation we will perform in separate step. Is it that allowed?
Yes. Yeah, you can do that. Okay.
Excuse
Now
me.
let's say, yeah.
Sorry to interrupt, sir. Sir, you said if you are working on R2, then next time you cannot work on
No,
R2.
no, I'm not saying that. I'm not saying that. I'm saying don't work if you're performing an operation on R2 in a step. Do not perform this. Do not perform it on. If you're performing two operations at once, then do not perform this both of the operations on R2 or something like that. Okay, that will be incorrect. That will lead you into trouble. So perform one operation at one. That is what we take.
Okay,
I will give you an example.
simultaneously, we can't do 3 minus 3 R1 minus 5 R1.
3 minus 3.
No, no, sir. The you do row 2 minus 3 R1, and simultaneously you are doing row 3 minus 5 R1.
No, this is fine because I'm not changing. I cannot do this operation. Let's say R3 minus 2 R2. This I cannot do because I'm changing R2 over here, and I cannot use that. I cannot use R2 to change R3. That is not allowed. Okay.
Okay, sir. Thank you, sir.
So, sir, the two operations that you're doing simultaneously should be independent of each other, right?
Yeah, they should be independent. Yeah. Okay. Now R3 plus 4 R2. If you do that, you will get 1, 2, half, 0, 1, 11 by 4, 0, 0, 35 by 2. And then you can perform, because now third row is also has no non-zero entry. So this will be the non-zero term. Okay. So you will make this term the leading entry. So how will you do that? You will, what you will do, you will just multiply it with 2 by 35. Okay. If you do that, you will get 1, 1, 1. All the diagonal entries are 1. All the non-diagonal entries are non-zero. So you will get an upper triangular matrix. And now, what is the determinant of upper triangular matrix?
Product of diagonal elements. That is 1 here.
Correct. Right. So you will get 1.
Sir, so
All right.
every REF or RREF matrix will have determinant 1.
Need not to be.
Okay.
Sir, in RREF, all the other elements other than 1 should be 0, right?
Yes, this is REF form. This is not RREF. If you want to convert into RREF, you need to make entries top of leading entry 1 to be 0. That is another, but we don't need to do that because we are just working with.
Okay.
Yeah.
So one more doubt. So if we were to convert this into RREF, that 1 and half, sorry, that half would not be changed.
Sorry.
If we were to convert this into RREF, so
Yes,
only the
determinant won't be changed.
4.
Excuse me, sir. What is the determinant? This last upper triangle matrix.
Yes. So determinant here is 1, right?
Just three, sir. Diagonal entries, sum of diagonal entries.
It is the product of diagonal entries, right? So you can tell whether the determinant of the matrix is 0 or not. So you can use matrix row reduction, row reduced Echelon form to tell whether the matrix has non-zero element or zero element. Whether the determinant is 0 or non-zero. You can use that to say that.
Excuse me, sir. One last. Can you explain sir question and this method?
Right. And now how do we calculate determinant of A using this? So now determinant of A here is determinant of determinant of the matrix is 1. All right. So determinant of this matrix is 1. Now you can trace back. So multiplying a row with 2 by 35 is same as multiplying your determinant by multiplying your matrix R, multiplying your determinant. That means 1 by 35 by 2. Basically the inverse of that. All right. And now now this doesn't change. If you add any two rows, this doesn't change as we saw. So it will not affect. So here it will again be. So determinant of this matrix will be determinant of this matrix will be 35 by 2. Now determinant here will again, here it will not change. Now here, what will it determinant? It will be determinant here will be multiplied by 2. So 35, earlier it was 35 here. So it will be 35 times 2, it will give you 35. All right. And then again, in these operations, it won't be changed because we are performing these row operations. It won't be changed. So again, here it will again be 35. And then again here, when you go back to from here to here, it is again 35. And when you come back to the initial matrix, you will get 35 multiplied by 2 because you are multiplying by 1 by 2. So inverse of that is 2. So we multiply by 2. So you will get 70 as the result. Okay. So you need to trace back your determinant.
Hello.
And if you are, yes, if you are, just give me a minute. And if you are interchanging anything, you need to multiply. If you are interchanging row, you need to multiply by -5 to that determinant. That is what, that is how we calculate determinant of a matrix using the row reduced Echelon form.
Sir,
all right.
Sir, just one question. That when we add any multiple of row to another row, the determinant does not change. Suppose when we are tracing back, we are adding 2 by 35 of R3 to R2. So by that logic, the determinant should remain 1 only.
No. When you are multiplying your row by a scalar, then determinant changes. Okay. We had saw that last time. But
No,
when
last
you
time we
add,
saw that. Last time we saw that when we are adding any multiple of a row to another row, then the determinant doesn't change. So multiple of
yes,
a row means only we are multiplying a scalar to another row. Means
yes.
suppose
But this is not. But this is, look. This is what is this? This is not adding into another row. It is multiplication. I'm multiplying a scalar to a row. This is different than addition. This is addition. I'm adding R2, 4 times of R2 into R3. This is not same as this thing. This does not change the determinant, but this does change the determinant.
No, like suppose we perform the step together, like 2 by 35 of R3 plus R2 from directly from the last step. Like we have the upper triangular matrix, and from the upper triangular matrix we perform the operation 2 by 35 of R3 plus 4 R2. So by that way the determinant shouldn't change by the rule we learned.
No, it will change, because when you are performing, I would suggest you go back to that rule and check. So,
Sir,
so
can you?
what I'm saying is that you
Yes.
can multiply this operation. Okay, this operation does not change the determinant.
So we are doing this operation only.
No, we are not doing. When you are saying what you are doing this operation, and here j is not equal to I. Note that. Okay, in this operation, what you are doing this operation. You are doing Ri going to Ri plus some d times Ri plus c times Rj. So this is not same as this. First of all, because you are multiplying something to this, and then this is you are adding two row operations. So I have said don't do that. Okay, you need to perform each operation separately. You can add other rows multiple to one row, other rows multiple. You cannot add same rows multiple to itself. That is same as scalar multiplication. Okay.
Sir, please discuss an example of Gauss elimination method.
Yeah, I will come to that. Let me complete with this. If you guys all are comfortable with whatever I said, so you can what you can do. So you can use this method to calculate determinant. So you can first reduce your matrix, square matrix, to an REF form, and then once you do that, you trace back the determinant. Okay. So how does it change? So let me write it down. So if your operation is interchange, Ri changes to Rj, that means it changes the effect on the determinant is determinant of A is equal to minus of determinant of B. Okay. If you multiply a scalar that is not equal to 0, then the effect of change in determinant will be 1 over C of determinant B. Okay. And if you perform a row operation, you add something like this, then the determinant remains as it is. So you can convert your matrix into an REF form, and then you can trace back the determinant. So for example, you're performing this operation over here, multiplying by 2 by 35, you will multiply 35 by 2, which is the inverse of it, and then so on and so forth. Here it will not change. So by going back this step, you will not change the determinant. Going back this step, it will change because you are multiplying by half, so it will multiply determinant by 2, and so on and so forth, and you can trace back your steps, and you can compute the determinant. All right. Okay.
So what is the
So
advantage of doing it in this form? We can normally calculate as you taught in week 1, right?
yeah. So okay. So if I give you matrix of, let's say, 5 cross 5 order.
Oh, okay.
Now you see the difficulty, right?
Hmm.
So it is always for 2 cross 2, 3 cross 2, it is fine, but for higher order matrices, it will be difficult.
So could you repeat this step while tracing this 2 into 35 by 2, we get 35. So we multiplied by 2 because it is R divided by 2. This is the reason.
Yes. R was divided by 2. So we are going backwards. Okay. So by coming forward, we divided by 2. So now by going backwards, we will multiply determinant by 2.
Okay. Then we
So basically,
have,
what you can do, you can think of that you are, yeah. Please continue. Whatever you say.
So yes, continue. You tell us.
No, it's fine. You asked me a doubt. I was about to just repeat the same thing, so it is fine.
So this is actually then we have 30 by 2. Then we have 35 backward. This is
Yes. All right. Now let me take an example of Gauss elimination.
So here we basically converted the original matrix into REF.
We converted original matrix into REF, and then we trace back the steps of row reductions to calculate the determinant of the original matrix.
Then, sir, here the determinant would be 70.
Yes, determinant of the original matrix is 70.
Okay, sir.
You can also check by calculating determinant over here. but let's leave it to you guys.
Sir, can you scroll it above?
Up?
Yes, sir. I want to see that line. Or do it some bit more. So scroll it down, sir.
Down.
Sorry, scroll it up. Scroll up. Scroll it up. Sorry. So once more, sir.
Okay. This.
So this, yes, sir. This R1 changes to R1 plus CRJ. This is what I was looking.
It's not R1. It is RI.
RI. Sorry. RI.
Yeah. I is not same as J.
Oh.
So whenever you perform this operation, you don't need to change the determinant. Whenever you have multiplied your Ri with a scalar, your determinant will change. In the backward steps, it will change to 1 by C, multiplying 1 by C to the matrix. Whatever determinant you have earlier to that. That is what.
Thank you, sir.
All right. Okay. Good. Now let's see an example of Gaussian elimination, and then we can call it a day. All right. So suppose you have this system of equation which is of m cross n type. All right. Now you can convert. How do I obtain an augmented matrix for this? So this is what I mean by augmented matrix. You add your column vector, your constant column. You add that into the coefficient matrix. Okay, and then you will obtain the coefficient matrix. Here was a matrix of 2 cross 3. Okay. So this is your coefficient matrix. Now I have added this column vector, column matrix, and I'm treating this new. I got a new matrix which has 2 rows and 4 columns. All right. So in general, what will happen? So you will have some m cross n matrix, which is a coefficient matrix, and then after doing this, and you can convert it into an augmented matrix, and you can obtain this with an additional column. Okay. Now this is how we'll obtain augmented matrix. Now this augmented matrix, I will perform these row reductions. Okay, that we just discussed. I will perform these row reduction operations on this, and in order to convert my A into an RREF form. All right, I can either convert into RREF form or REF form. REF form is also fine, or RREF form is also fine. RREF form will give you further simpler expression of the matrix. So it will help you more. Okay. So then once you convert that, now the solution set of this new system, which you will get. So you will perform the row operations on column vector B also. You will obtain some new column vector C. Okay. And then you can rewrite this as system of equation to be Rx equal to C bar. Okay, something like this. All right, you can write it as Rx is equal to C. Now the solution set of this system is same as solution set of the original one.
Sir, but the question is how to find the solution of Rx equal to C.
Yeah, I will come to that. So we have already seen it is direct. Once you have the RREF form, it is direct to. You can just write down all the independent variables in terms of the dependent variables. Dependent variables in terms of the independent variables. We saw that an example, right?
After writing that, after writing all the dependent as independent, then what do we do?
That is a solution set.
Okay.
Yeah, that is your solution set. So I will discuss an example. Let's say I will take this example itself. Okay, and let me write out the complete solution. And once you have this, once you have reduced to this system, then you can write down all the solutions of it. So RREF form or RREF always have solutions. So they always have solutions. So now let me take this example itself. All right. So let me take this example 3111032. So 3111032 and what else? So this is the augmented matrix. Now, what should I do first?
So first row should be divided by
3.
Correct. So R1 changes to R1 divided by 3. So it is 1, 1 by 3, 1 by 3, 1 by 3. All right. And
So
second row
this
remain as it is.
augmented matrix we just took as an example.
Yes, this is an example. Okay, now what do we do?
The second row to be divided by 3.
Correct. Second row we can divide by 3, and we will get 1 by 3, 1 by 3, 1 by 3, 0, 1 by 1, 2 by 3, 2 by 3. All right. Now this is an RREF. This is an REF form, right? Now I have obtained a matrix. So this matrix is an REF form. Are you guys agreeing with me?
Yes.
Right. Now I can stop here and I can write down the solution. Okay. Now what are the leading entries? So leading entries. This is one leading entry. This is another leading entry. So what are the corresponding variable? So because this is first entry, it is x1. It's in the second column, so this is x2. It corresponds to x2. The third column leading entry will correspond to x3, but there is no third column leading entry. All right. So x1, x2 are the dependent variables. Okay. So the leading entry becomes the dependent variable. So these are the dependent variables. And x3 becomes the independent variable. Okay.
So we had x, y, and z as the variables. So are we
No.
still taking?
Oh, x, y, z. Okay. Okay. So sorry. So then let's take x, y, z. Thanks. X and y and z is the independent variable. All right. Right. Now you can write down the corresponding system. So your
Sir,
matrix
the
is,
position of the column is basically the suffix of the variable.
yes,
Of the
yes,
dependent variable.
yes.
Sir, could you please show the equations once? I think I copied wrong the question.
I will do that. You can take notes from the. I will share these notes, so you don't need to note.
Just
note
for
it.
1 second, could you please scroll? I think I've copied wrong. Just 1 second.
Let me finish, please.
Okay, sir. Okay.
Yeah. Okay, so you have this matrix. Now you have B prime. Okay, you don't have the same matrix. You have B prime. So now let me write down the system of equation, which is 1 by 3, 1, 1 by 3, 2 by 3, x, y, z equal to 1 by 3, 2 by 3. Now what is the corresponding equation? So it will be x plus 1 by 3, y 1 by 3, z equal to 1 by 3, and then 1 by 3, sorry, y plus 2 by 3 z equal to 2 by 3. Now you can write down your dependent variables, which were x, y, in terms of the independent variable. So first I will write y in terms of z. How will I do that? So clearly y is equal to 2 by 3 z minus 1. All right. Can everyone see that?
Yes, sir.
Good. Now I can write my x in terms of y and z. So 1 by 3 minus 1 by 3 z minus 1 by 3 y. Now I can replace my y in terms of z. Now I can replace my y in terms of z. So let's do that. All right. So I can take 1 by 3 common. It is 1 minus z minus 2 by 3 z plus 2 by 3. All right. So I will get 1 by 3, and then it is 3 minus 3z. Sorry, 3 minus 3z minus 2z plus 2 divided by 3. It will give you 1 by 9, 1, 5. I can take 5 out, 5, and then it will be 1 minus 1 minus 1. Okay. So now what is the solution? So the solution set of A is x, y, z. Okay. So what is x now? X is 5 by 9, 1 minus z, 2 by 3, z minus 1, and z, where z is in R. So this is my solution set. Set these vectors will be the solution. So this is my solution set of the matrix. Okay. So this is how REF form helped me to write down dependent variables in terms of the independent variables. All right.
Can you please scroll up?
Yeah, Sambhavi, you do you have any question? You have raised your hand. So yeah, scroll up like this.
No, to the top of the document.
Okay.
Sir.
So we are using a straight line in the middle of the matrix. So is it the general way to represent that?
Yeah, this is called augmented matrix. These are special matrices. These are augmented matrices coming from the system of equation.
Sir, just for 1 second, could you please show the question? I think I had copied wrong. Just 1 second. I will take a screenshot.
This is the question itself.
No, the augmented matrix, the system of equation from which we got that. The original question we are referring. Means did we do the augmented matrix of this equation only?
Yes, yes.
Okay, thank you. Okay, sir, thank you.
All right, is it clear to everyone? Yeah.
For that augmented matrix, we have to use that straight line in the between.
Can you repeat your question? I couldn't understand.
For this augmented matrix, we are using a straight line means at the between the last column and the second last column.
Yes,
so
yes,
we have
yes.
to use that.
So this last column is special because this last column corresponds to the constant terms. That's why we are separating this. And the first matrix corresponds to the coefficient matrix. That is what I said earlier. So this column, so this system has any given system can be represented by AX by B. Okay, this is AX by B. Now I can use this A and B. I can write it down together in a matrix like this. Okay, and to separate which one is coefficient matrix and which one is constant matrix, I'm using the vertical line. Yes, Bipul.
Sir, the augmented form, that is 1 and 2, that is not, we are not considering it as a dependent or independent variable, right?
No, they are not. They are not. They are the constant matrix.
They are the constant. Sir, last two steps, if you can just repeat one more time, sir.
Which last two steps?
Last. I mean, down. Yeah, here, sir. I mean, how are we getting the solution set to it? I think.
So till this point, it is fine, right? Till this point, is it fine? Till this point,
absolutely fine, sir. Absolutely fine.
Right. Now, what I've done, I've just multiplied this matrix with XYZ.
Okay.
So if you do that, you will get this system.
Okay, got it.
They are same thing. Now, once you get this system, now you write down Y in terms of Z, because that's the first thing you will do. You will write Y in terms of Z, because dependent variables are written in terms of the independent variable. So that is what you do. So you get this Y, and then you use the first equation to write down X in terms of Y and Z. Now you already know value of Y in terms of Z, so you replace that and you get X in terms of Z only. Okay.
Okay, sir.
Now you can further do one more thing. So because we have converted till REF form, that's why we stop at REF. So that's why we need to again rewrite X in terms of Y and then again rewrite Y in terms of Z. But instead of stopping at REF form, we can go one more step further. We can go to RREF form. Okay, and we can make this entry to be 0. Okay, so let's start with this point. So we have 1 by 3, 1 by 3. So we have 1 by 3, 1 by 3, 1 by 3, 0, 1, 2 by 3, and 2. 2 by 3, 2 by 3. So we stopped at this point in the previous thing, and this is in the matrix because this matrix was in REF form. But we can go for one more step further. We can convert it into RREF form. And how do we do that? We can apply this operation R1 minus 1 by 3 R2. Okay. So 1, 0, and then 1 minus 3 minus 1 by 9 times 2. 2 by 9, right? And then 1 minus 3 minus 1 by 9, 2 by, so the same thing. And then second row remain as it is. All right. So what we will get? We will get this 1, 0. This is 9 and 3 minus 1. So 1 over 9, right? Zero, 1, 2 by 3, 2 by 3. All right. So now what is, now if I write it down in terms of the, so my R will be, which is, let's say R prime, it is 1, 0, 0, 1, 1 by 9, 2 by 3. My B prime, let's say my B double prime is 1, 9, 2 by 3. And if I write down the corresponding system of equation, which is R x bar equal to B double bar, then it is going to be x plus 1 by 9 y equal to 1 by 9, and y, sorry, z, and then y. So let me write down the matrix 1, 0, 0, 1, 1 by 9, 2 by 3 multiplied with x, y, z equal to 1 by 9, 2 by 3. Okay. So it is x 1 by 9 y or y by 9 equal to 1 by 9. Sorry, z should be z by 9. And then y plus 2 by 3 z equal to 2 by 3. So what we will get? We will get x is equal to 1 by 9 minus z my 1 by 9, and y is equal to 2 by 3 minus 2 by 3 z. So again, the leading variables were first and the second column. So it is x and y were the leading variables, and z will be the, so these will be the dependents, and z is the independent. All right. So I can express dependent ones in the terms of independent. So you can check that this answer that you got obtained from this, it is different in a bit. Have I made mistake?
So there should be 1 minus z.
Yes, Joy.
Yes, I had mainly two doubts. Could you scroll down a bit?
Yeah.
Yeah, so this is the final matrix, right? Like we cannot simplify it further, right?
Yeah, this is the RREF form. We cannot go further.
Okay, okay, sure. And then the second doubt is, which I have here, is like uh, we considered z as the independent matrix, independent variable, because
Variable.
there are no ones in the z column, right?
Yeah, it doesn't correspond to a leading entry. Yes.
Okay, so like it becomes dependent if there is a one corresponding to that column, and if there is no one corresponding to that column, it is independent.
So just no. So think of, so the correct way to say it is, if that if a column has a leading entry, then variable corresponding to that column, because the independent is the dependent variable. So whichever column has leading entry, so the variable corresponding to that will be the dependent.
Okay,
So
so if
for
there
example, you can have a matrix like this. So this is an example only. So this is in RREF form, right? But
yes, sir.
the first column and the second column, first column and the third column has leading terms. So the variable corresponding to that means x1 and x3, they are the dependent ones, and x2 is the independent.
Okay.
Okay. Right.
Okay. And is it a must like we should represent the other dependent variables in terms of the independent variable?
Yeah, that's why the terminology, because it is an algorithmic way. So that is why we are doing this.
Okay. Okay.
Yes, Meghna.
So when we have calculated y previously, there I think one minus sign is missed out.
Yeah, maybe. So I will update these notes and I will let you know.
So actually, y is 2 by
By the
3 into
previous
1,
method,
1
we
minus
can
z.
see the solution set by the
Sorry?
REF method. We got we for x we got a different solution, and by the RREF for x we got a different solution.
No. So there is a computation mistake. You will get the same solution. I've done some computation mistake. I will update that while uploading notes.
Okay, and the second question is, if RREF is the simplest form, then we should always do the solution by RREF only. Means, do we at all need to stop at the REF?
No, it is your choice.
Okay, no, or it can vary from question to question.
As it will be up to your convenience.
Okay. And so here also the solution we obtain, that is not any particular solution. It is kind of a general solution, like whatever value of z we put according
Because
to
it has
that.
infinitely many solutions.
Sorry.
It has infinitely many solutions. Whenever you have independent variable, you will always get infinitely many solutions.
But sir, in this matrix we cannot perform the determinant only, so we cannot get the determinant of a equal to 0. So how can we say that it has infinite solution?
That is what I'm telling you. If you have independent variable, okay, if your RREF form has independent variable, what does it mean to have independent variable? So it means to have independent variable. That means, for example, in this case, there is independent variable. You can write z is the independent variable. So whenever there is an independent variable, you will have infinitely many solutions to the system of linear equation.
Sir, so from what we saw now, it means any m cross n matrix can be converted into RREF, and then we can solve the system equation. So any system equation in which the variable and unknown are not equal, they have infinite solution.
They have been fixed solution. No, it is not. This is not a fixed solution. You can find out the solution. What do you mean by fixed solution?
No, I am meaning infinite solution. Like
Need not to be infinitely many solutions.
Because we can put infinite values of z, and then.
For example, let me give you an example. You can have RREF form of this type. Okay. Yeah. So, or maybe you can have RREF form of this type. So in this case, this is also RREF form, correct?
Yes.
But how many solutions? There are two dependent variables, which is x and y, but it has only one solution. It doesn't have the infinitely many solutions because there is no independent variable.
So when in RREF there is at least one independent variable, there will be
yes, then it will be infinite many solutions. Yes.
And it's an independent variable is the one which is not the non-zero leading element.
Which is not the leading entry.
Like in this RREF, the two ones that we have, they are the dependent variable, and the independent variable is what can we say? The dependent variable, what I understood. The independent, which can we choose?
So once you know the independent variable, once you know the dependent variables, other variables are the independent ones.
Okay. We have to see by the column number. Like in the first column has a dependent variable, so x is a dependent variable, x1. The second column also has dependent variable, so x2 is a dependent variable. The third column we don't have any non-zero one entry, so the x3 will be independent. Is it like that only?
Yes.
Or there is any other common way?
No. So whatever variables are there, so whichever column has the leading entry, variable corresponding to that column will be the dependent variable. All the other variables are called independent variables. All right. If a variable is not dependent, then it is independent. Got it?
Okay.
Right. Sambhavi, you have anything to ask?
Yes, sir. Actually, the previously we calculated y. There some mistake is there. Y is 2 by 3 into 1 minus z.
Where? Can you tell me where it is?
Here, y value of y is 2 by 3 into 1 minus z.
So where you have put the
arrow.
arrow.
Right. It's not 1 by, got it. Okay, it's not 1 by z. It is z. It's not z minus z. It's 1 minus z. Right. Right. Now, if I substitute this back into here, then it will be minus z, and then it will be minus 2 by 3, and then plus 2 by 3 z. Right. And then it will be this plus, and then z will be removed. So it will be 1, 1. Yes. So 5 will not be there. It will be 1 minus z. Right. 1 by 9. Right. Oh. Thanks.
Yes, sir. Thank you.
Yeah. Thanks for correcting me. Okay. So this is the Gaussian method. It would have been great if I could have solved more example. But let me quickly tell you one more example, okay, which is more like an exercise for you. So I will leave the details for you to figure out. But you can also end up at the inconsistent solution. So the system of linear equation may not always have a solution, okay? So when in what cases you can end up having no solution, you can also find out that by using this row reduced echelon method, this Gaussian method. So first of all, for example, think of this system of equation which is of this type. Okay. Now, what is the corresponding augmented matrix? Corresponding augmented matrix looks like this: 1, 1, 1, 2, 0, 1, minus 3, 1, 2, 1, 5, 0. Now, I will apply the row reduction to convert this coefficient matrix into RREF. But these row reduction will be applied on whole matrix. Okay. So what I will do, so it is already, first row is already in leading, second row is also in leading entry position. So I will substitute this. So I will R3 minus 2R1. I perform this. So I will get this. First rows remain as it is. First two rows, third row will be 0. And then it will be minus 1. And then it will be 5 minus 2, 3. And then minus 2, minus 4. All right. Now, you see that. Now, what can you see? You can see that the second row, the third row, is same as the second row, minus 1 multiple of the second. Okay. So what you can do, you can subtract that. So you can do that R3 minus 2R1. Sorry, 2R2. Sorry, R3 minus R2. Okay. So you do that. And what will you get? You will get 1, 1, 1, 0, 1, minus 3. Second row will remain as it is. First two rows remain as it is. Third row become 0.
It should be R3 plus R2.
So plus
Yes, sorry.
R3.
Yes, sorry, thanks. So we will get minus 3 over here. But now you see that you have a 0 row here. You have a 0 row over here, but there is a non-zero entry over here. Okay. So in the constant matrix column, you have a non-zero entry in front of a 0 row of the coefficient matrix of RREF. So this tells you that the solution, the system does not have any solution. Whenever you come across this RREF, this form, then you can tell that the system has no solution.
Sir, but we can again on the third row divide by minus 3, and then we can obtain the 0, 0, 0, 1.
But that will not give you anything.
So can you please repeat the last word which you just
So for example,
just right now.
So let me so if you write down it into the matrix form. Okay, so what is your R matrix? Your R matrix is 1, 1, 1, 0, 1, minus 3, 0, 0, 0. Right? What is your new B prime? What is your new constant matrix? It is this. Right? Now, if you write it down in terms of system of equation, then it is like this: x, y, z equal to 2, 1, minus 3. Okay, is everyone fine with till this point?
Yes, sir.
Right? Now, if you write down, so what is the first equation? It is x plus y plus z equal to 2. Second equation is y minus 3z equal to 1. What about the third equation? What is third equation?
No equation at all.
2x1 plus
0
x2 plus y.
Sorry. What is third equation?
There will be no
0
equation.
x plus 0 y plus 0 z is equal to
0 is minus 3.
No equation.
So it is 0. 0 on the left we have 0. What about on the right?
Minus 3.
minus 3.
Okay, so now is third equation making sense? Can 0 be
No.
equal to some non-zero number?
No.
No, right? So there cannot be any solution to this system. That is what it says. So whenever you have this kind of inconsistency, this is called inconsistent systems. Inconsistent. So whenever you have this kind of inconsistency, you will say that the system has no solution. All right.
Sir, so in
So
the
RREF form. So the RREF form also help you to tell you that when it doesn't have any solution. All right. Yes, Neil.
Sir, so in the augmented matrix, if the A matrix has a 0 row, but the constant matrix has even one non-zero in the last row, then it will be inconsistent.
Corresponding to 0 rows of RREF form, there should not be any non-zero entry. Okay, in front of a 0 row, there should not be any non-zero entry. If there is a non-zero entry in front of a 0 row, then the solution system will have no solution.
Okay.
All right.
Okay.
Okay, so RREF forms are useful. Okay, so someone was asking in the beginning why RREF form, because RREF form are helpful. It tells you, it gives you solution to a system of Lie equation. Okay, it also tells you what kind of solution you get, whether you get infinite solution, unique solution, or no solution. Okay, type of solution also. And it also helps you express the solution in terms of variable. Okay, so it helps you to express, solution set. All right. So that's why this Gaussian method is very important for yeah.
Sir, please write that. Sir, please write that step for where you told that what is an inconsistent system.
Yeah. So this is inconsistency. Whenever you have an augmented matrix correspond to, there is a non-zero entry correspond to a 0 row. Yes, Mahima.
Sir, if the R is 1, 1, 1 and 0, 0, 0 and then 0, 0, 0.
Okay.
And then B prime is 0, 0, 0. Then there
This
is
is what your R is?
Yes.
Okay. And what is your B?
0, 0, 0.
Right. This is fine.
Yes.
Yeah, so
Then
what is your question?
about the dependent, how should we write the dependent variable in terms of independent
So you
variable?
tell me how many dependent variables are there? You tell me how many, what is the leading entry?
One dependent
How
variable.
many, first of all, tell me how many leading entries are there?
One.
There is only one. Which one?
Yes.
The first corresponds
The
to
first
first
column.
column one. So it is x1, right? Or whatever
Yes.
x or y, whatever there is there, corresponding to this column. And what are the independent variables? Second column and third column, that is
Second and
x2
third
and
one.
x3. All right. So you can express x1 in terms of x2 and x3. That is what you will do.
Yes.
So your solution will be x1 is equal to x2 minus x3 minus x2 minus x. This will be the answer. Yes, Amol.
Sir, can there be a case where we have the solution is that we have not an inconsistent solution, but still we don't have, still we don't have any solution? Can there be any case? For example, like if three planes are there
No, if
and they are
if
on
the
a
solution
parallel.
is consistent, if the solution is consistent, then
Yes,
you will
yes.
always have a solution.
So what if we have three planes in 3D axis?
Yes.
So they are all parallel.
Right.
So what will happen to that thing? We have that equation. We will be having equations, but they don't intersect with each other.
Mm.
So supposing there is when we study in fluid mechanics, all these things, so there is a
Yes,
laminar
yes. So I
flow,
understood your question.
kind of a laminar flow. Over there is a layer, then layers of flow, and what will be that solution? What
Yeah,
kind?
yeah. So let me take an example. So let's say you have an R2, you are in R2. So you
Yes,
have
sir.
this line which is passing through origin.
Yes, sir.
Which is, let's say, x equal to y is equal to x.
Yes, sir.
Okay. Okay. So now you have another line which is parallel to this.
Yes,
But
sir.
shift it some bit. So that means it is intersecting, let's say, at 1. So,
Yes, sir.
so the equation will be like it is the slope is 1 and x minus 0, it is passing through this x minus 0, and then y is equal to y minus 0, so it is y minus 1. So the equation will be y minus 1 equal to x. So there are two equations like that. So they are parallel to each other.
Yes, sir.
All right. So let me write down the system of equations. So system of equation is x minus y equal to 0, and
Yes,
the
sir.
another system is x minus y is equal to minus 1. Correct?
Yes,
So
sir.
y plus 1 equal to x, that will be.
Uh, y minus 1 is equal to.
It's okay, sir.
No, this is correct. This is correct.
Okay, okay.
So this is correct.
Right. So now you write down the corresponding system. What is the corresponding augmented matrix? It is 1 minus 1, 1 minus 1, 0 minus 1. All right.
Yeah. Yes, sir.
Now you convert. Now the second row is multiple of the first row. So you subtract it.
Yes,
So you
sir.
do R2 minus R1. You will get 1 minus 1, 0, 0, 0, minus 1. So you
Yes,
get
sir.
inconsistent solution.
Yes, sir.
Inconsistent. So it will always lead to inconsistent solution in the augmented.
Okay. Okay.
So if it is not inconsistent, if it is consistent, so a system is called consistent if it's not inconsistent. If it is consistent, then you will always get a solution. That is
Okay.
it.
Thank you, sir.
Yeah. So we have used yeah. Okay. Now there is one more point that I would like to. I know it is getting late, but let me finish off what is the
Sir,
last topic.
sir,
Yeah.
can you scroll up? Here, sir. X1 is equal to minus x2 minus x3. Can you explain that one more
Yeah.
time?
Again, you will just write down this x1, x2, x3 is equal to, just write it down in terms of the system of equation, right? And then it is 0, 0, 0. Now you multiply. You will get what? You will get this equal to 0. This is the only equation that you will get.
Yes.
So now write down x2 minus x3.
Okay.
Now you can also use these row echelon forms to compute the inverse of a square matrix. All right. How do you do that? So let's say you have a matrix A. Okay. And you want to convert it into, you want to find out a matrix A inverse that is equal to I. Okay, that is what we want to do. So now how you can think of this problem? You can think of this problem, let's say A is your matrix, and then you have a vector X vector over here. This is your second vector Y. These are the column vectors of A inverse, let's say. All right. And then you have these column vectors. Okay, so let's take these 3 column vectors. So now suppose you have some matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. So how will you multiply? So this will multiply it with this, will give you the first entry. This will multiply it with the first column, will give you the second entry. This will multiply it with the first column, will give you the third entry. So you can think of this as a system of equation that x with x bar is equal to this column, right? Similarly, you can think of y into a into y bar is equal to the second column. Similarly, you can think of a into z bar is equal to the third column. All right, so you will get this system of equation. Is it fine with everyone? How do I get this? This is just a simple observation. Multiplication of 2 matrices correspond to this. Okay, so this is how we'll get. Now we want to find out inverse of A, which is same as finding out the.
Understand.
Huh?
Like I understood in the part that we assumed column vectors for A inverse. After that part, I could not understand. How did we?
When you think about it, you will understand. So now we have these
briefly,
three.
Could you please tell?
You pinpoint which point did you didn't understand, because
Like I understood
because I'm keep on repeating myself multiple times, and then still you have the same thing. So it is yeah, it is taking time. So you know matrix multiplication, okay? Are you comfortable with that?
Yes, yes.
Okay. So how do you obtain this first column? Can you tell me how do you get this first column? By multiplying which column of A inverse, let's say.
We multiply the first row of A with the first column of the X.
Only the first row? Just the first row?
Yes, sir. The first row with the first column.
But this will give, that will only one entry. That will give you first entry. That will not give you the first column of A, of I.
Yes, sir. It will only one entry.
Okay. So this entry you will obtain by multiplying the first row with the first column, right? How will you obtain the second entry of the first column? This entry.
Second row with first column.
Yes, second row with the first column. What about the third entry?
Third row with the first.
That is what I have written over. Isn't it?
Excuse me, sir.
Okay, understood. Thank you.
Got
Sir?
it? Similarly, you can do the second and the third. Yes, Shelly.
Sir, actually, I got disconnected. So this point, which you write, X bar, Y bar, and Z bar. So this is A inverse. Means you suppose
Yes.
A inverse.
These X bar, Y bar, Z bar are the columns of A inverse.
Columns of A inverse. Okay, sir. Okay, sir.
Okay, and then you can write down this problem as solving these 3 problems, three system of linear equation. All right, and you can find out the solution of each one of that. All right, by using the row echelon form. You can convert it into row echelon matrix and you can solve that. But instead of doing separately, what we do, we will do it all together, because converting A into row echelon form is just a like one-time thing. So the same step you will follow to do for the second system, the same you will do for the third system also. All right, make sense? So we will do all together. So what we will do, we will write A and we will write the vertical column. We will have X, Y bar and Z bar. That is equal to sorry. Yeah, so how do we do? So we will write the first column here, second column. So this is the first B1 column, right? Second B2 column, third is the B3 column. So I will write all 3 columns together. Okay, B1, B2, B3 columns together. And then I will convert this A into row echelon form, this REF form. Okay. And I will get whatever I will get over here, that will be the A inverse of this, because this RREF form will always be the identity matrix. Okay, that we discuss at one point of time, because if I work with square matrix, then all the leading entries, all the diagonal entries, all the leading entry will come on the diagonal entries, and all the other non-diagonal entries will be 0. So you can do this exercise. Yeah, this is only true when your determinant of A is non-zero. Okay, so for that only you will calculate the inverse, right? So you start with this hypothesis that the determinant is non-zero, then you are calculating inverse. So it is similar to work with this. Methodology is that you will start with this matrix. You will write down your matrix A here, and then you write down matrix I, and then you convert your A matrix to RREF, and you apply the same row operations on the on these matrices as well as you do in the case of by solving this thing, and then you will obtain the A inverse on the right and R in R here. So let me quickly take an example. So let's say this 1 1 1 2 4 8 3 9 27. This is your A matrix, and then I have this 1 1 0 0 0 0 0 0 over here. Now I apply what I will apply first, R2 minus 2R1. Okay, so and R3 minus 3R1. So I will get 0 0 1 2 6 4 minus 1 8 24 3 1 over here. All right, 1 0 0. First row remain as it is. Second row become minus 2 1 0 minus 3 1 minus 3 0. All right, now I divide second row 2 1 1 1 0 1 3 0 1 3 1 0 0 minus 2 minus 1 0 1 half minus 3 0 1. All right, now
Divide by 3.
R3 minus R2.
oh, but this just a second. Oh, sorry. I have done a mistake over it. Sorry. So R3 minus 3 R1 I'm doing. So I will get R3 minus 3 R1. So I will get 6 and then 24 over here. Yes. Sorry. Yeah. Yeah. All right. So let me divide R3 also by, so let me divide R3 by 6. Right. I will get 1 1 1 0 1 3 0 1 4 1 0 0 minus 1 half 0 minus half 0 1 by 6. All right, and then you can do R3 minus R2 1 1 1 0 1 3 0 0 1.
Yes,
Right?
sir. 1.
1 0 0 minus 1 half 0 1 by 2 minus 1 by 2 1 by 6. Right, and then you can convert into RREF form. So you subtract R1 minus R2. Okay, and then you do R1 minus R3. And okay, let me first do R2 minus 3R1. Okay, and then R1 minus R2, and then I will do R1 minus R3. Okay, I will see what will I get. So let's do first R2 minus R3 becomes 1 1 1 0 1 0 0 0 0. So I will leave it to you guys to solve this part. R1 minus R2 1 0 1 0 1 0 0 0 1, and then this R3. So we'll get 1 0 0 0 1 0 0 0 1. So we'll get something over here which will be correspond to A inverse. Yeah, this will correspond to A inverse. All right. Okay. So let's stop here.
Yes.
And you can ask your doubts in TA sessions. They will be discussing your doubts. All right.
So when is your next class, and what will be the topic of the next class?
So next class will be on Sunday. I will not take that class. Some other instructor will take that class. I think Lavanya will take that class.
So what will be the topic?
And topic for
it will be
discussion?
week 3. Week 3. You can check what is in week 3.
Okay.
Will be week 3 will be start. So this today week 2 ends. All right. Thank you guys. So let's stop today's discussion.
Sir, could you please send these notes?
Yeah, I will share.
Now, will you share in calendar only or some other place?
Yeah, calendar. You will find in live session notes.
Thank you. Thank you so much.
Yeah.
Okay, thank you, sir.